All right, so we'll try that one again. Are there any questions? All right, so let's talk about vectors, addition to vectors. And part of the reason I'm doing this, I've got a video on this more explicitly. You've done this before last semester, but for some reason, the next lab that you're going to do is going to involve addition of vectors, and too many students seem to fall apart, not sure what to do. So I'm going to try one more time. One more time, not necessarily for this group, but I'm going to try again, like I've done for every semester, to go over this, and hopefully this will be the group. This is the group that's going to understand and not make anything other than a careless error on the lab. So let's put a negative charge here, and I've got a positive charge here. And I want to figure out what is the electric field at this point, and I'll just call it point P. So the electric field at point P. Well, I have two charges there, and let's make them more explicit. 1 microcoulomb and -1 microcoulomb. Actually, just to make the life easier, take a nanocoulomb.
That makes it easier.
It will. I need to give some dimensions here. So let's say the distance between the two charges is 10 centimeters, and the distance to here is 6 centimeters, and this distance we will make 5 centimeters. That does not look right. Make it 4 centimeters. All right, question says to what the problem is.
We don't have all the sides.
Excuse me?
We don't have all the sides.
No, as in the problem I'm posing to you, not the problems with what I've given you so far. No, I've given you everything you need to know. I think, if not, we'll figure it out when we do. All right, so I have two charges, each producing its own electric field. The positive charge is exerting an electric field at point P in which direction? All right, let's see, groundswell, see if we can get a third person to put the finger in the right direction. All right, we got 3, got a 4. It's as if it's the correct answer. All right. So the electric field, I'll just label it E plus. Actually, probably EP plus. And the direction of the electric field because of the negative charge.
The opposite, they're like.
No, not quite. Yes and yes. What do you know about electric fields and negative charges? Sorry, what do you know about electric fields created by negative charges? Okay, or towards the negative charge. Yeah, so it will be going in that direction. And I'm going to label that EP minus. So it goes away from positive towards negative. Now, which is going to be bigger in magnitude? Larger in magnitude, the positive or the negative electric field? And why?
The EP positive.
Why?
It is closer.
Yeah. What's the formula for electric field? From a point charge? From a point charge.
It's distance times.
I'm not quite sure you're gonna recover from that one, unless you divide by distance later or something.
Equals KE. U.
Do we have a marker here that doesn't suck?
Degree of yours is returning.
KE, I heard that part.
Q. And then, now is this Q1 and Q2?
Is it?
Yes. Yes. No.
There we go, okay.
And then all over R2. Or R to this, R to the,
R squared?
R squared, yeah.
Yeah. That's what kids are calling it these days.
Yeah.
And then one last bit.
The direction is R hat.
All right. So we have this generic equation. This is the formula that you use for the electric field if it is from a point charge. Now on the test, I will probably bet that you will have a situation where you have an electric field from something that is not a point charge. So, please, only use this formula if you're dealing with a point charge or something that can be approximated as a point charge. All right, and this is where the away from positive towards negative comes from, because if Q is a positive number, then the electric field is in the positive R hat direction, which means away from the center. And if Q is negative, then the electric field will be in the negative R hat direction, which means towards the center. All right, so I have two vectors here. I can come up with an angle and come out with in polar notation, but we need to add these two vectors. So, unless you want to get into law of sines, law of cosines, and some of you might, because that's just the way you roll, we need to get these in rectangular notation. So I'm going to go ahead and establish the brainwashed I hat to the right, J hat up. If for no other reason is that in the lab I set that as the convention. Just because it makes it easier to grade if everybody uses the same convention. And in case you missed it, that should be heading straight towards there, and this is heading straight away from there. All right, so first let's get the magnitude of the two. So KE, we know. Q, I gave to you. R. Let's figure out R. R is the distance. So this is R positive, and this would be R negative. How would you find it?
Trigonometry.
Okay.
For the R positive, it would just be 6 squared plus 4 squared.
6 squared plus 4 squared is equal to R positive squared. And so therefore we get R positive squared to equal
52.
Since it's an R squared on the bottom there, I'm just gonna leave it like that for now. We will need the square root in the moment, but it's good enough for now. All right, so let's just continue on that one. So we've got this vector going off in that direction. The magnitude is K, 9 times 10 to the 9th, Newton meter squared per Coulomb squared, times Q, which is 1 times 10 to the negative 9th coulombs, divided by R squared, which is 52. Units?
Centimeters? Oh, I thought you were saying for 52. For the whole thing?
Yeah, no, for the 52. You stopped at centimeters, so I did the hand gesture of and going square.
Dr. Fox, isn't that the other electric field, the one that's 52?
Oh, this one?
Yeah.
No, recognize that 52 is R squared, not R.
Yeah, but wouldn't it be that one? The one on the left?
No, because we had this triangle right here, where that is 6, that is 4, and so this would be the square root of 52.
Oh, I'm sorry, I thought we did. That's good.
Do you think a careless error would be made in class? Is that what I'm hearing? Whoever taught you 151 warped you. All right. Now we're going to run into an issue here with units because I got a meter squared and I got a centimeter squared. We probably should get them in terms of the same thing. Probably this one's easier. What is this in terms in meters squared?
5.2.
Or 0.52.
If you're stopping there, then
Meters.
no, that was not the main issue there. Meters to centimeter, or centimeters to meters, how far you move to the decimal point.
2. Oh.
If I'm doing centimeters squared,
4.
I have to convert each one. If you just move it over 2 places, you're left with centimeter meters, which is a bizarre unit. So to put it into meters squared, 0.0052. All right, so we end up with on top, and this is why I said the nanocoulombs might be more convenient, is because I have a 10 to the 9th and 10 to the negative 9th. Those cancel out, or multiply to get 1, and I'm left with 9 over 0.0052, which somebody's about to tell me what that equals. Oh, I thought you just did it. Okay, you just want to wait to be the one that confirms?
I didn't want to be the first one.
Go bold.
1730.77.
Anyone else get that?
Yeah.
All right. See, there you go. Works like that there. Whoever speaks first is always going to be right. Isn't that the way it works?
I wish.
What are the units?
Coulomb meter squared. Coulombs per meter squared.
If you're starting out, Skylar, with newtons, then so far so good. If you're ending with newtons, then you know. There we go. If we look at the units there. Shouldn't there be a red? We'll pretend that's red. That Coulomb cancels out with one of those. That meter squared cancels out with those. I'm left with newtons over coulombs. Just a quick note that the electric field is newtons per coulomb. That's something that you should know cold, like force is newtons, charge is coulombs. All right, so we now have the magnitude of it, but we need to figure it out in the directions. What is the horizontal and vertical components? So when you are doing this, please make sure you get the magnitude first before you break it up into components. Unless you are so comfortable with this that you can cut out some steps.
Now, we found the magnitude for the entire problem.
No, we found the magnitude for E. This is the magnitude E, P positive, magnitude.
Got it.
questions? Let's break it up. All right, so I know that my vector is going off in that direction. I have a ratio of 6 to 4 to the square root of 52 in multiple colors. And my electric field will be in a similar triangle. I have a magnitude of 1731, and I'm trying to figure out, that's a right angle, that's a right angle. They're similar triangles, I'm trying to figure out this and this. You can set it up like a ratio. You can try to be more sophisticated and bring in some trig terms. Technically, if this angle here is theta, then it's going to be negative 1731 cosine of theta plus 1731 sine of theta. Whoa, there's a mistake here. What is the mistake?
You didn't put the unit vectors?
Say it
You
again?
didn't put the unit vectors?
Exactly. I had J hat. All right. Now, we don't actually need to figure out what theta is. You can if you want, but that adds just one more place where rounding kicks in. I know that cosine theta, that angle this only has one. That angle there is theta. Cosine of theta is the adjacent or the hypotenuse. And so this becomes negative 1731 times 4 over the square root of 52. I hat. Plus 1731 times the opposite of the hypotenuse, 6 over the square root of 52. J hat. If you want to find the angle and then use the cosine sign, have at it. And now someone is going to tell me those values. First one, I'm thinking somewhere around negative 900.
First one's negative 960.186.
Negative 960. Point what?
186.
I'll round off. I hat plus, that would be here, plus
1440.3.
All right, why would I take off points for this?
You don't have the direction?
I've got the I hat, J hat, and they're defined here.
Units?
Yeah. All right, so units would be,
Newtons per meter, or newtons per coulomb.
yes. Now, where you put the units, this is sort of a refresher for the units. I didn't leave much room here, so I'm gonna throw the marker onto the ground in protest. I put parentheses around the whole thing and put newtons per coulomb there, newtons per coulomb there. Or if I want to distribute it, that's fine, 960.2 newtons per coulomb. I had plus 1440.3 newtons per coulomb J hat. Either one is an acceptable answer. If you want to write it only once, you do need to have the parentheses. Otherwise, if the parentheses go away, the newtons per coulomb is just attached to the second term. Now granted, if you drop the parentheses, do the first form, drop the parentheses, it's not a major error, but I've had some people lose a letter grade over being nickel and dimed over petty stuff. Actually, 2 letter grades. Anyway. Questions on how we got this?
So we just took the original ratio, like the 4 and the 6, and we just did that over the new hypotenuse we found.
Yeah, yeah. The physical triangle and the electric field triangle are the same, or similar. Same angles. All right, now we've got comfort there. Let's get the second one. We can nail this one quickly.
Is that whole bottom line 10? Including the 4, on the triangle thing?
That's,
No, this one. You wrote 10 centimeters, is that the whole thing?
yes, 10 centimeters from here to here. All right, what is the magnitude? How do we find the magnitude of EP negative?
Is it the same equation? Or it should be the same equation?
Yeah, other than what's different?
The sign. I guess the direction?
For finding the magnitude. What's different between this and what we just did?
R squared's gonna be different.
All right, so we have 9E9, 1E negative 9 over, what is the distance now?
72 centimeters squared.
All right, 72 centimeters squared, because our triangles are 6 by 6.